Yeah, now you can start.
Okay, so yeah, yeah. So hi, hello everyone. Uh, Good evening and good afternoon also. So this is the third lecture of this event, and our speaker for this session is Dr. Prerona Chatterjee. She is a visiting faculty member in the School of Computer Sciences at NISER Bhubaneswar as an assistant professor. Welcome to you, ma'am. Uh, Okay. She earned her BSc from St. Xavier's College, Kolkata, and MSc in Mathematics and Computing from IIT Guwahati, and holds an MSc and PhD in Computer Science from TIFR Mumbai. She also attended MTTS in 2015. In this talk titled "How Hard Is to Solve This," she will discuss which of the following problems is more complicated: adding two five-digit numbers or multiplying them, and how theoretical computer science tries to solve such problems in a formal way. So let's ma'am, as you have attended MTTS before, so maybe you can speak a few words about your experience in MTTS and how MTTS has helped you. So over to you, ma'am.
Uh, yeah, I'm audible. Yeah. Okay. Yes. So yes, I attended MTTS in 2015, and it was, I think, quite interesting to see how, like, math is can be done like in groups, and how discussions among people who are trying to learn math together is so helpful in understanding the concepts of math better. And I remember, like, so two of us had gone to MTTS that year from IIT Guwahati, and I remember after that we tried, like, we like got our friends together, and we basically told them how important it is to like discuss math with each other while we are learning. And I remember we used to do that after having attended MTTS, and indeed continued doing that. I continued doing that during PhD. And yeah, I mean, just the experience of MTTS, understanding how discussions with each other while learning is so important to learning and understanding better. That was, I think, the biggest takeaway I had from MTTS, and it was very helpful. Of course, apart from that, I got to meet many other people. Some of my friends from undergrad and stuff who I had lost contact with, I met them, and I also met some new friends, and that is of course there. But even just if you focus on understanding math itself, that also the experience was really great. And yeah, I mean, yeah, after that I did PhD, and basically during PhD I shifted from pure math to more of what is called theoretical computer science, which is essentially the math behind the CS, all the CS that goes on. And in this talk, I won't actually be telling you, I mean, okay, I will, apart from so in my abstract, it was there that, which of the two problems which of the two problems seems more complicated to you, adding numbers or multiplying numbers, right? And intuitively it feels like multiplication is a harder problem to solve, but then how do you formalize this feeling, right? And questions like this is what theoretical computer science tries to solve, or at least try to understand. And in this talk, I will essentially be giving you a brief idea of what this area is, okay? Because I don't think it is. I don't think this subject is something that is taught in most undergrad or master's program even during math. So I would just like to give an overview of what this area, the kind of problems this area looks at, and how we try to solve these problems. Okay. And this is going to be, or at least I have designed it to be, a very interactive talk. So I really need people to answer questions when I'm asking. Okay, otherwise it won't work. Okay, so please answer when I ask. Okay, so let's start. Yeah. What happened? Why is it? Okay, so let's start with a problem. Okay, so suppose you are given some cities. Okay, let's say villages. Okay, how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 villages. Okay, and what you want to do is you want to connect all. So currently, if you see, they are all disconnected. Okay, and what you want to do is connect these villages to each other. Okay, so how do you connect them? You connect them by road. Okay, so this is a road, this line joining this village to this line joining it, or an edge, is essentially going to be a road connecting the two villages. Okay, and now you want to connect all the villages to each other. Okay, so suppose I now add this extra edge from this. Can you see my pointer?
Yes,
Yes.
ma'am, we can see.
Yes. Okay. Okay. Yeah. So if I'm joining this road from this village to this village, then I would also say, I will also say that this village and the bottommost one are also connected. Okay, via this road. So you first go to the village on the right, and then you go to the village on the bottom. Okay, so when I say connected, it need not be a direct road between the two villages. It just, there should be a path from each village to the other. Okay, that's what I mean by connected. Okay, so every time you add a road, you connect some new villages. Okay, you have 8 villages in total, and you want to connect all the villages to each other. Okay, so you want to connect all the villages, and so what do I mean by connected? There should be a possibly indirect road between any two villages. So take any two villages, there should be a road which connects the two villages, possibly indirect. Okay. And now let us assume that the cost of constructing any direct road between two villages is 10,000. So for now, let's just assume that, so we won't worry about the fact that some villages are maybe possibly closer to one another than another. We just assume that every road, so any road between any two village, will cost you 10,000 rupees. Okay, so the question is, so suppose you have been given the task of connecting the villages, and there is some there is some higher some authority who has told you, okay, this is what your task is, and you have a budget of 50,000 rupees, connect the villages. Okay, so can you do it?
Prerona ma'am, just 1 minute.
Yeah. Yes.
So can you switch on your video in other side? Means now in YouTube your video is not visible.
Oh, I see. Okay, I'll do the other one. I see. Okay. Is this better?
Yeah. No, can you try? Yeah, now
Okay.
continue. We'll see.
Yeah. Okay. So do you understand the question? So there are 8 villages. You want to connect all the villages to each other, possibly by indirect road. Each road costs 10,000 rupees. The authority has told you that this is your task. 8 villages, connect all of them. Each road costs 10,000 rupees. You have a total budget of 50,000 rupees. Question is, can you do it? So can you do it? What do you think? Okay, this is the question. Can each pair of villages be connected to each other with 50,000 rupees? Each edge, each road costs 10,000. So maybe, okay, yeah. If yes, how? And if not, why not? Okay, how much budget would be enough? So maybe let's ask a simpler question. Is 70,000 enough?
Yes, ma'am.
Yeah, okay. Why? Why do you think so?
Because we have 8 villages,
Yeah.
so we can just connect the pairs.
Yes. So
In a line.
in some order, we just connect one by one. So if we go back to the, so we have already connected 2, then let's just connect this, then this, then this, then some order. Okay. In some order, you just connect so you've reached some point, you just connect it to an unconnected village, and you can do it in 7 lines. Okay, so 7 edges. Okay, that means 7 roads. I can do it in 70,000 rupees. 70,000 is enough. But is it necessary? So you feel, okay, firstly, do you think that you can do it in 50,000?
No, but I don't have a
No, right.
proof or
So the
something.
feeling is yes. So you would feel that 50,000 is not enough, because you tried to do stuff and you realize that no matter what you're trying to do, you need at least 7 edges or 7 rows. Okay, so you want to now convince the authorities that, dude, 50,000 is not enough. I need 70,000. Okay, but then how do you convince them? So let me again ask maybe another question. Do you think, so you had eight villages, right? So do you think 30,000 would be enough? That is, can you connect 8 villages using just 3 edges?
Definitely not.
Definitely not. Why?
Because there are 4 pairs.
Exactly. So there are 4 pairs at least. So 3 edges you can't connect 8 for sure. Okay, that is, but then I want to now prove that actually you need 7 itself, not 3 but 7. Okay, how do you do that? So let's try to abstractly see what's happening. So let's think of each of these villages to be in different components. Okay, so each villages are in different components, and each time you add an edge, you are essentially so 2 villages then will now get into one component. Okay, so they are connected, they become one component. Okay, others are still in separate components. Okay, is that clear? So now what is the end goal? So we connect one more edge, again that also gets added into the component. What is the end goal? The end goal is that you want all of it to be connected. All of it has to be in the same component. Right? Do you see where this is going? Can you, using this idea, can you complete the proof now? You had 8 components. Each time you're adding an edge, what is happening? The number of components is reducing by at most 1, right? So if you are connecting villages which were already connected to each other, then the component isn't reducing. Number of component isn't reducing. But you do have the potential of reducing the number of components. That is, the number of components is reducing by at most 1 at every time you are adding an edge. Is that clear? So you started with 8 components, you want to get down to 1 component. Number of components is, okay, so in general, number of components is n. At the end, you want to get to 1 component. Each step, the number of components is reducing by at most 1. Okay, therefore what you get is that the number of steps you need is at least n minus 1. Okay, and that is how you convince that 70,000 is actually necessary. You can't do it with 50,000. Is this idea clear? Okay, so this is basic. Yeah, so this is sort of a very simple case, but this is how proofs in theoretical CS looks like. Okay, I mean, of course, very simple proof, but yeah.
So 70,000 is necessary and sufficient, no?
Yes, necessary and sufficient, exactly. So very good. This brings up this idea of an upper bound and a lower bound. Okay, so 70,000 is an upper bound on the cost that is required, but 70,000 is also a lower bound on the cost that is required. Okay, so very good. So it's sufficient but also necessary. Here the two match. Okay, we'll see that in general these are the kind of questions which come. Okay, so okay, now you will say that of course if you're given a problem, then solving it in a better way is of course useful. Taking less resource to solve a problem is useful. But what I told you is basically a way of proving that something is hard to do. Okay, so now you would ask me, how is proving something hard helpful? Okay, why? So again, as we will see, that this is also another question which theory CS people look at. Not only do we try to solve problems faster or with less resource, we also ask, is this necessary? Okay, is this much resource necessary? And you would ask, why is proving something like that helpful? So there are some reasons, because there are actually problems which in its full generality is hard to solve. Okay, I will give you some examples, of course, but they are hard to solve. But the point is that researchers don't stop when they see that something cannot be solved. The point is that once you realize that something is hard to solve, you always try to ask further questions, like, is it so you were actually trying to solve some problem, but is it always necessary to find the exact solution? Okay, so for instance, there's this problem called traveling salesperson problem. So now you have again some cities or villages that the salesperson wants to travel. Okay, in this question, you assume that there are direct roads for every pair of villages. Okay, and but here the roads are of different length. Okay, so if the person travels from this village to this village, for instance, the road is longer, so they will have to take extra time, more petrol, whatever. So the length is longer, so resource needed is longer if you travel from this to this as opposed to this to this. Okay, and so the salesperson wants to visit every village, okay, exactly once, and return back to the village that they started from. Okay, so now the question is, find the route which minimizes the distance. Okay, so now this problem is actually very hard to solve. Exactly, that is, if you ask, give me an algorithm to find the shortest route which does this tour, it is not possible to solve it exactly. But then we don't give up. What you say is that in many cases, in many real world applications, what you want is not necessarily the shortest path. Okay, what you are maybe happy with having an approximately shortest path. Okay, so this is a sub area of computer theoretical CS, which basically tries to solve problems in an approximate manner. So whenever there are these important problems that you would like to solve, you can imagine that these are, I mean, it's very easy to see that this is a real world problem. You want to find shortest paths in some setting. We believe that this is not solvable exactly efficiently, and therefore you ask, maybe we can't find the exact solution, but can we find an approximate solution efficiently? Okay, and in general, this area is basically tries to deal, so these optimization problems where you want to find the best route, the best time, the best, so these LP type, when these maximize something with some constraints, right? You would have seen these LP type solutions, these problems. So any such problem where you want to maximize some function with some restrictions, these are the kind of problems that are studied in this area. And you can't guarantee efficiency, okay, when you want to find the optimal solution, but you want to give a solution that is close enough to the optimal efficiently. Okay, so for instance, this metric TSP, which I just described, metric traveling salesperson problem, it's hard to solve exactly, but it has an efficient 1.5 approximation algorithm. Okay, so you can't give the best solution, but I can give you a solution which is at most 1.5 times the best solution. Okay, so this is one area called approximation. Then the next reason why you would want to, why you would want to know that something is hard is that, okay, and again, you now understand that some problem is hard to solve. And again, what this allows you to do is then ask yourself again, do I actually need the most, do I need a solution to the most general problem, or is there some additional restriction that I can put for the application I have in mind? Okay, so many of, again, real world problems, many of the times, once you realize that the general problem is hard, you realize that the problem that you actually want to solve, that I actually want to solve, is actually not the most general version. It's the general version with some restricted, with some additional restrictions. So again, let's see a example. So you have a graph again, some villages or anything that you can think of. Okay, so these are again connected to each other, not by direct roads. Okay, but they are connected. And what you want to do is you want to basically make sure that all the villages are safe. Now, how do you want to do that? You want to place some police stations in some villages so that each road is guarded by a police station. Does that make sense? So for instance, if you put a police station on this village, then this one can guard this road, this road, this road, this road, this road. Okay. Is it clear? So you want to place police stations so that all the roads are guarded. And now, so it's easy to see that this, for instance, if you place a police station on these two vertices, then it guards all the roads. Okay. And the K vertex cover is, so yeah, okay, K vertex cover, that's the name of the problem. You want to find out if there are, if it is possible to place K police stations. So given a graph, is it possible to place K police stations and get all the roads covered? Okay, that's the question. And yeah, and of course the output should be which villages do you construct the police station on. Okay, and again, this problem is actually very hard in general. Okay, so it takes like exponential time, so it's inefficient. So any algorithm that you can think of to try to solve this is inefficient. Okay, but then you say that is it the most general problem that we are trying to solve, or is there some restricted problem that is enough to solve for us? And it turns out that indeed in many cases it is the case. So again, what this sub area of theory CS is called parameterized algorithms, where it is a way of dealing with problems where some input parameter is small. So for instance, in the K vertex cover, so again, in general, it's a hard problem, but when the parameter that when the parameter you care about is small, then we can guarantee you efficient algorithms. Okay, so for instance, in the K vertex cover, it is believed to be it's believed to be hard if both K and N are large. But if I promise you that K is small, then actually there are ways of solving the problem efficiently. Okay, so in general, knowing something is hard to do often allows you to modify the question in such a way that you can now start solving the problems. If, of course, the modification is important to you, like, so if I gave you a problem, you realize it's hard, then what it tells you is that, okay, let me come back to the problem that I posed to you and see if there is a simpler problem. Is there a restricted version that I can ask, or is it okay if I have an approximate solution as opposed to the actual optimal solution? So in these cases, many a times they can be solved. These are two examples of sub areas which tries to do that. Okay, then the most closest to my heart reason for asking these lower bound questions I will come to that, but before that, again, let's try to solve another puzzle. Okay, so suppose you have a group. So okay, so let's say you have there are 5 of you, and each of you think of a 2-digit number. Okay, and what you want to do is, as a group, you want to find the sum of the numbers. As a group, find the sum of the numbers that you have each selected without so sum of the numbers without any of you finding out what the numbers are that the other people have selected. Okay, do you understand the question? So 5 of you are there. Each of you have thought of a 2-digit number. You want to find out the sum of the numbers that you have thought of without figuring out what numbers the other people have thought of. Can you think of a way of doing it? Okay, is the question clear? So far, yeah. So there is a number A1, A2, A3, A4, A5. So each of you should, at the end of whatever protocol, find out A1 plus A2 plus A3 plus A4 plus A5. But the first person should not know A2, second person should not know A1 or A3, and so on. So so the ith person should not know anything about AJ for J not equal to I. But you want to find out the sum A1 plus A2 plus A3 plus A4 plus A5 together. Okay, this is the question. So let me give you a hint maybe. Okay, so I'll tell you that the first step of the protocol is that the first person is going to add their number. So they will pick a random number, okay, random 2-digit number, let's say, and then add their number to that random number and will tell the sum to the second person. Is it clear what the first step is? First person will take, so first person will take a random number and add it to whatever their number is, A1, and tell A1 plus R to the second person. Okay, can you now tell me how to go on? What should A2 do now? Okay, firstly, so now that A1 has told this small A1 plus R to A2, does the second person, does capital A2 know anything about small A1? Do you think they will know anything? No, right? Why? Because it has been garbled by this random. Right? So now what should A2 do? Let's say A2 does this. They will add whatever number they got, small A1 plus R, and add small A2 to it. Okay, and tell this sum to the third person, capital A. Is it clear what this step is doing? Does A3 know anything about the first number or the second number?
No.
No, right? Again, because of that initial randomness that had been put in, neither does the second person know anything about the first person's number, nor does the third person know anything about the first or second person's number. Okay, so is it clear where this is going? So now what will A3 do? A3 and A4 will also do the same thing. They will add their numbers to this number. So A3 will add small A3 to whatever they have got, give it to A4. A4 will add small A4 to whatever they have got, give it to A5. Okay, and then finally, what should A5 do? A5 should do the same thing, add their number, send it back to A1. And now, how do you get the sum?
Remove the random number, minus.
Remove the number. So the first person will just subtract the random number and then reveal the sum to the second. Okay, is everyone happy with the protocol, in the sense that are people convinced that no one will get to know anything about the numbers just because of that initial randomness that had been put into the mix?
Yes, ma'am.
Okay. Yeah. So yeah, just take a minute or something or a few seconds and just convince yourself that nobody gets to know anything about any of the other numbers because of that initial randomness that had been brought in by A1. And also not that capital, so the first person doesn't get to know anything about the other numbers either. Only thing they know is the sum, okay, which anyway everyone was supposed to know. So that's cool. Okay. Okay. So now that we have that, let us now come back to my favorite reason for studying lower bounds, which is that in the previous example we saw a situation where there is no way for any of the other people to know the numbers, okay? But let's say, so what we want to do is, let us say that we know that a problem is hard, okay? So now because this, because this problem is hard, so suppose you have an adversary, okay? Now the adversary can't solve this problem because this is a hard problem, okay? So can we use the fact that the adversary can't solve a hard problem to create something good, create some secure protocols, okay? So let's give an example. Suppose there are three of you, okay? Three of you are there, and so suppose I don't know, the first person wants to send a message to, so let's say you're in a classroom situation, okay? And let's say Dhruv is in one corner of the room and Sita is in some other corner of the room, and you have Bhumika in the middle, okay? So Dhruv, if he wants to send a message to Sita, has to pass the message through Bhumika, okay? So suppose you are in this situation. Okay, so you have Dhruv wants to send a message to Sita, but they don't want Bhumika to find out what that message is. Do you understand the situation? So Dhruv wants to send something to Sita, has to send through Bhumika because they are far apart, and but they don't want Bhumika to figure out what that secret is. So how do you do it, essentially? Okay. So again, let me give you some hint. Okay, so suppose Dhruv actually has a box and has a lock and key with him. Okay, and let's say Sita also has a lock and key with her. Okay, this is what the setup is. Here, A wants to send secret message to C, has to send through B, does not want B to know the secret. How does one do it? That's what I want you to answer. But let me give you a hint that that person A has a box and a lock and key, and person C also has lock and key. How do you find out how do you send this message? Are there any ideas? What would be like what is the first thing that you would try? So let's say person A will lock the key, lock the box and send it. Okay, let's say puts note in the box, locks it, gives it to B, B gives it to C. But then now what? C doesn't have key to the lock that A has. Okay. So firstly, why is the first step okay? Because B does not have the key to the lock that A has, right? So then B can't open it. Okay. and B gives it to C. But then C can't open it either, right? Because C does not have key to the lock of A. Right? So what does C do?
Maybe we give some numbers to those messages, and maybe some keys, some adding 2 or 3, and shifting those letters to that position and send it to C.
No. Don't have to go into number. I'm giving you a physical lock. So A has a physical lock and key. C has a physical lock and key. Don't have to figure out what the lock and key is. They actually have lock and key. Okay. And they have this box. A has physically locked the box, sent it to C. C has a different lock and key, but doesn't have key to the lock of A. What will C do? But sorry, so you were saying something about numbers and mailing it somewhere. So there's no mailing or anything allowed. It's like, assume that you are in a classroom. Okay, so there is, yeah, I mean, literally, you are in a classroom. 2 people who are in 2 corners who want to send message. So has to go through the middle person. Okay,
Ma'am,
that's yeah.
C puts their own lock.
Yes.
A was the same.
Yes.
C puts their own lock, returns it to A. Then A
Yes.
will unlock it and they will come to
Very good. Very good. Right? So C will put their lock and give it to B. B will give it to A. Okay. Then A will remove their lock because they have the key, and then give it to B. And then B will give it to C. C will unlock and reveal the note. Okay. Very good. So this is what is actually called the Diffie-Hellman key exchange program. So where does this come up? So this comes up. So suppose you are, so what is this A, B, and C actually, right? So you are A, and C is the server of the bank who you want to talk to, right? But then what is B? B is basically all the wires through which the message is going, okay? And the thing is that people can see what messages are going through the wire. Someone, if they want, can see the message going through the wire. But you want, okay, so what is the thing? So firstly, if you and the bank has decided some way of encrypting this message, then you know that even if there is this B person who is looking at the messages, will not be able to decrypt. But the first time you and the bank server is talking to each other, you have to first decide on some key which is going to be used for the encryption, right? So, okay. So, the first time you talk to each other, you have to figure out a password or something secure, which from now on you are going to use each time you communicate. But how do you figure out this secure password or secure way of communication? The way you do that is using such a protocol, okay? And secondly, note that last time when we were doing this, trying to find sums of the sum of numbers without any of them finding out each other's number, there was no way for any of them to figure out the sum. But in this case, this protocol is secure only if you assume that B does not have some way of breaking the law. For instance, if B had this big hammer or something, or what is it called, this thing which breaks the locks, right? If capital B has this equipment, then they could have broken the lock and stolen the key, okay? But we have to assume that B is not so powerful. That is why am I saying all of this? In real world, what you have to assume is that there is a problem which is too hard for a human being to solve, or for Turing machines or whatever, for computers to solve in limited amount of time. Okay, that is why lower bounds are important. Okay, so you use the fact that some problems are hard for people to solve in limited amount of time, in limited amount of using limited amount of resource, and using the fact that this is hard, you end up coming up with protocols which will ensure security. Okay, so in particular, the whole area of cryptography is essentially just a study of techniques which techniques to communicate with each other in a secure manner in the presence of some adversary. Okay. And whatever we just described is essentially this Diffie-Hellman key exchange protocol, which is what the key that is exchanged between two parties before, so before you actually start talking to each other in a secure. Okay, so this is what is called this public key cryptography. So in private, so there are two kinds of cryptography: private key and public key. Private key is where you have physically met each other, exchanged some secret, and then using that secret to talk to each other securely. Whereas there are ways in which two people can do this Diffie-Hellman key exchange to just decide on this secret without actually meeting. This is what is called public key cryptography, and this was the most this is what started this whole area of public key cryptography. And so of course, when you're actually talking to some bank server, you don't have physical locks and physical keys. The lock and key is a function which is easy to compute. That is, you can again think of a lock where if you have the key, it is easy to lock. Okay, but if you don't have the key, it's hard to unlock. So you also have these key locks, right, where you just press the thing and it gets locked. So even without a key, it's easy to lock it, but without a key you can't open it. It's hard to. Okay, not like you can't, but it's hard. Okay, so that is what the lock looks like, and the secret would actually be a function such that it has this property that g of x comma fy is equal to g of y comma fx, and whatever, so x you can think of is the message of a, f of y is what c is going to send a, fx is what a is going to send to c. So because even though it's happening through b can't figure out what f is. Okay, and this g of x comma fy is the secret. So that is the secure note which was there inside the box. Okay, so yeah, I hope it's somewhat clear. But I think the main point I want to drive across is that it is important to prove hardness of problems, because if you know that certain problems are hard, you can then use the fact that these are hard problems to come up with secure protocols even in the presence of adversary. Because even to the adversary, that's a hard problem, right? So what is, I mean, these were like some specific sub areas of theory CS that I spoke about. But in general, what is this area? It's essentially, there are problems that we want to solve, often coming from real world applications. I mean, you look at the real world, model it mathematically, and you want to solve that problem. And because these are all mathematical models, it is like, so you want this mathematical model to so I mean, and as I said, it's in the real world, you want to model it mathematically, but it will obviously have some restrictions, right? So for instance, because it's coming from the real world, you don't have infinite amount of time. You only have whatever your lifetime to be able to do anything, right? Or you don't have all the space in the world. You have some whatever the best computer can give you, right? Whatever the best RAM access you have, that is the amount of space you have. Okay, so you are modeling the real world scenario. So so whatever it is, it will have you're modeling the restrictions and you're modeling the abilities that you have. And in this model, you want to solve the problem which is coming up. Okay, this is what you have. And then the question that you want to study is how much resource is needed for this model to solve the problem. This is the main question that theory CS people want to study. Okay. And now, very broadly, theory CS can be divided into two groups. Okay. One is that there are researchers who are interested more in just solving the problem. The kind of when I said that okay, you realize that this problem is hard to solve, and then you ask, okay, I don't want to solve that problem in the most general setting. I'm okay with solving it approximately. I'm okay with solving it with where the parameter is small. Okay, so they are more interested in just solving the problem, not so much about I will change the model, I will change the situation in which I want to solve the problem, but I just want to solve the problem. Okay, this is one group of people who are called people who work in algorithms. Okay, so this sub area is essentially algorithms people. Okay, so for instance, you want to find the factors of a given number. You want to find the shortest path between two vertices in a graph. You want to find the next best move in a chess game. Okay, these are all, as you see, are coming into AI. You want to find out whether the given image is that of a cat or a dog. You want to find out you want to predict the next word which fits best in the sentence, which is LLM, okay, or ChatGPT or whatever. Okay, so you have a problem that you want to solve. I am okay with changing the model, but I just want to solve the problem. This is very broadly algorithms research. And then there is the other group, smaller group, who are more interested in understanding the model. Okay, so you have these various models of computation. You have communication models, like we saw, right? There are these, so two-party, multi-parties. There are two parties who are talking to each other. There are multiple parties who are talking to each other. And then you can, you can assume that there is no, the channels or there is no corruption between in the communication channel. So for instance, where we were doing the sum of numbers, finding out sum of numbers, we assume that when you are telling each other something, there's no miscommunication happening. You are actually, whatever you want to tell the next person is actually hearing that itself. So there is no compromise in the channel. Okay, so uncompromised channels. But then you can also have compromised channels, like we saw in the next one, the cryptography setting, right, where there is somebody who's watching and seeing what is being sent and would like to cheat you. Okay, so that's a compromised channel. And then there are these broadcast channels and point-to-point. So point-to-point meaning that you are actually talking to each other. So one person talking to one person, and you have broadcast like it's happening on a TV or a radio, where one person is broadcasting to everyone else in the group. Okay, so there are these multiple communication models, and then so what you want to do is understand these models. What are the problems that can be solved efficiently by the models? What are things that cannot be solved efficiently by the models? Okay, so the model is more important. Then of course you have computers, general purpose computers, which in whatever we call it Turing machines. You have quantum computers, you have circuits, you have proof system. Okay, there are many models that you would like to study, and the question you want to ask is, what are the problems that can be solved? And the first group is where you have important problems that you want to solve, and you just ask, in what setting can they be solved? Okay, so these are the two kind of questions broadly that you can ask. First group is algorithms research, second group is complexity theory research. Okay, and I work in the second group. Okay, And in particular, the most of my work till now has been in this area called algebraic complexity theory, where you are same question there are some problems that you want to study, some models that you want to study, and what are some of the important problems. You want to find factors of a number or a polynomial. You want to compute determinant of matrix, multiplying two numbers. I mean, you would be surprised to know that actually most of these problems we don't really. So in the first example that we saw, someone I think Dhruv only very nicely said that that was one problem where we knew that the upper and lower bound were matching. We could say that it can be solved using that 70,000 rupees, and also 70,000 rupees is required. But many of these problems, actually, there is a large gap between what the best algorithm is and how much we know at like the lower bound on the amount of resource that we think we need. Okay, and all of these are problems that on which people are working on currently, and we would like to bridge the gap. Okay, and of course there are the flip question as well, where you want to understand the power of algebraic models. Okay, so the most well studied is an algebraic circuit, where you basically have at the leaves some numbers, so field constants and underlying variables. And so any algebraic circuit will be computing a polynomial in the most natural way. And you want to, so polynomials show up in algorithms in like various algorithms, and what you want to do is succinctly represent polynomials, and you want to ask how succinctly can you represent some important polynomials. Okay, so what is the smallest circuit that you can come up with which computes your favorite polynomials, determinant of matrix multiplication. And there are some other models also which are studied. Yeah, and I would just like to sort of say the kind of research that happens in the computer science department at NISER. So there is secure multi-party computation, which I spoke about. There is algorithms design, which I spoke about, and some other ML sort of things, and of course complexity theories. Okay. So yeah, I want to sort of end there, and like, are there any questions?
So thank you, ma'am, for this beautiful lecture. So yeah, maybe we can take those questions if anyone have any. If anyone have any question.
Yeah, if anyone has any question about like the talk or general theory CS research or anything.
Yeah, so I am asking like if anyone have any question about this talk, and if they have anything to ask you. So okay, maybe people don't have any. So maybe in the very first that 8 village and road problem. So was there a crossing allowed, like crossing of roads and
Yeah,
like,
sure. Yeah, but
crossing is
no, what do you mean by crossing? As in like doing that and then taking this and go there? No, no.
Okay.
So I mean these have to be separate. Yeah.
Okay, fine.
Yeah.
Okay, so I think there are no questions like from audience or other.
Can
So
I just ask? So like I didn't know about this curry leaf initiative till you people asked me to give a talk. Can you tell me a little about?
Okay, maybe Bhumika will. Bhumika, are you here?
Yes.
Okay.
Hi, ma'am.
Yeah.
Bhumika here. I'm the one who texted.
Yes.
So yeah, like I think it's been 4 years that curry leaf has been formed, and I know we do it every year that during this particular time. It's Professor Kumreshan sir's birthday now in these.
Yeah. I saw. Yes.
It's also the formation of curry leaf. So we celebrate it together, and then we call invited talks from different
I
speakers.
see.
Yeah.
So, but this is open to like anyone.
Yeah,
Like,
yeah.
yeah, anyone. Okay. Okay.
Yeah.
And so all the organizers, they are MTTS alumni, and
Yes, the organizers
Okay.
are MTTS.
I see. So
And
which year were you in, and what are you doing now?
I was I think last year I completed my level 1, and before that level 0. So now I've taken a drop for MSc.
I see. Yes.
Yeah.
Okay. Nice.
Arigna, maybe we
Thank you.
can have a group photo now.
Yeah, fine. Can you take the photo? Because oh, I can see Bhava sir has raised his hand. So
Hello.
Hi. Yeah, it's
Yes.
after a long time I have seen you, Prerona.
Yes.
Yeah, good. I could not. Yeah, I mean, okay. Let me first talk to the people. Bhuvna, I mean, we are still on live. Probably you can stop, right?
Okay, shall I stop the live recording?
Yeah, I think you should. Yeah.
Okay, I'll stop them.